Introduce Amy Hodler and David Hughes. Okay.
Yeah.
Yeah, sure. And a little extra plug for the Graph Geeks community. If you happen, anybody here would be the graphs. I don't know, probably not a whole lot of those guys. If you would be interested in graphs, the Graph Geeks community is a place you might want to look into. I'm really excited about this topic. We hear about GraphRAG, how to bring graphs into your retrieval augmented generation. But what about different modalities, things like images? How do you get information from that? I can't even figure out how to finish that sentence in a coherent way, but they're going to actually show how to do it. So let's get it started.
Also here with David Hughes, the principal solution architect at Enterprise Knowledge as well, and many of you know David's been with me for this. So we're going to kick it off. I'm going to start with probably one of my favorite pictures, not just because it makes me laugh, but because there's a lot of nuanced information going on here. There's a lot of data here, actually. It's very subtle. Anybody here have kids? Anybody? Yeah, okay. So you can't tell me there's not a little kid somewhere in the background that is influencing this. However,
That was my 2 thoughts.
was that yours? Same thing.
I think those without kids are even more aware.
Yeah, nobody ever grows up. So what's interesting here is when I try to ask AI, I want a similar image. Or if I just do a Google search, it doesn't get that nuanced information that all of you chuckled about. It doesn't understand that there's more going on than just a toothbrush holder and a toothbrush here. So when I did a Google search on this, you can guess what I got. A bunch of sinks. I didn't get any dinosaurs. I didn't get any toothbrushes. Actually, there might have been, maybe in one of those there's a toothbrush. But it doesn't understand what the context is here. And when I asked Claude about it, so I was like, what is funny about this image? It thought for sure it was a joke about the T-Rex having short arms. I'm like, well, this is funny, but that's not it either. And so if I wanted to find something with a similar feel, a similar context, I would basically fail. Now, I could go through and do a whole bunch of searches. I could iterate on it. I could use large language models. I could use GraphRAG to say, hey, if it looks like this, don't go over here. If it looks like that, I want to retain it within, I don't know, something I've maybe searched for before. But again, we're not getting that latent image information. We're not interweaving different information like textual information and visual information together. And we're not getting the associations that you and I will have with this image is that there's something else going on, that this is funny, and this is probably related to a kid or someone who's just childlike. But also, if we don't know why we're looking for an image like this, we also don't get interpretability on the results either. And so if we're gonna look for something else, and I will say, let's say bananas, and I say, I'm looking for bananas on a wooden table. There's some other ways we could do that, and that's using multimodal GraphRAG to provide associative detail. So things that are associated but aren't just similar. So what multimodal GraphRAG does, as opposed to just showing us a bunch of images of bananas, which here we've got, if I said this is the result of give me bananas on a wooden table, and there's some decent matches here, but the better matches are actually on the edges. Why? What's different about it? Well, in the middle image, we have bananas as part of a larger recipe, or it looks like they're gonna cook something, eggs, interesting, and bananas, but you're making something else. And so it's not as good an image match as a 2 on the end, but I can't really tell you why with just a regular search. But when you bring in multimodal GraphRAG and you're able to look at the images and the components within the image, you get much better results. And that's because multimodal GraphRAG, someday we'll have to come up with a better term for that, breaks down these components so that we can explore them either individually or together in regards to texture, in regards to spatial placement and quality, how busy is the image. So the middle one's got a lot more complexity, doesn't it? So we want to be able to look at those both individually and together and look at images that are similar, but also have some guiding characteristics as well. And so this allows us to blend both semantic detail, semantic context, and the data from text, visuals, and other things as well, that enables us to reason at multiple levels of abstraction and context. So for example, one of the examples that I like is if we were, and we are working on audio as well. So if we were watching a movie and you hear a bird and you don't see a bird, you know there's a bird in that scene, right? But you don't have to see it to know it's there. But if you see a bird, you might add in audio as well. And so the greater context in associations is really important. David, can you tell us a little bit about images in RAG?
So our first approach was a naive approach. You may be familiar with OpenAI's clip model. You supply it with a caption, a toy dinosaur. You supply it with an image and you get back an embedding. The embedding's a 523 dimensional embedding, fairly robust, but you can only do associative search. If you click in or search for an image of bananas, you're going to find all the things that were back in the embedding space as being similar. But you don't have any interpretability on why are they similar, what are the features about them that are similar, just that they are similar. So that was our first naive approach, and for an early use case, it worked well. But we then had the question of what else could we do? So then we performed segmentation. First, we got the objects out of an image and realized, hey, we can start to decompose an image into its component parts and its primitives and really get a better understanding of what is in this image. Then we went and did things like textures, complexities. How many hard-shaped lines does it have? How many outlines does it have? Predominant colors. And then it hit us, because, you know, much like any kind of development effort, it's iterative, that if we have the bounding boxes, which have center points of all these objects, then we can start to do things like spatial analytics. The banana's to the left of the cup. The computer is below the faucet. Maybe not. But the ability to have spatial analytics, and that now, because we're doing a lot of agentic work these days, that now we can do associative search and provide a language model also with the context and interpretability of those associative search results. So that's the high level of what GraphRAG is.
Yes.
And Amy's going to tell you more about it.
So to dive a little bit, or at least start to dive into multimodal GraphRAG, the process in a nutshell, so this is kind of a nice way to think about the process. You start by decomposing, in this case, images, could be other elements as well, but you break them down into their subcomponents. And in this case, we're also generating captions as well. Then you create your graph. So your components and subcomponents now loaded into a graph. And this is where we preserve the context of those images. So the dinosaur to the left of, or depending on which your orientation is, to the left of the sink, the dinosaur on top of the table. And so preserving that context is really important. After we've decomposed to subcomponents and then we preserve the context with the graph, we now have to use an embedding space. So this space really creates the anchors for your global search in the graph. And it's the basics of our semantic search as well. So it's kind of the backbone between when you have the semantics and the graph, that kind of is your backbone. And then you have the multimodal context. So now we're able to look at those two different elements, kind of the semantics and the graphs, and then blend them together for our LLMs for a more full context. And this kind of gives us almost a hybrid knowledge space that we consider associative intelligence. And I think, you're going to go into detail, which I know everybody wants to see.
So look forward to any questions you have afterwards, but at a high level, we ingest in a image and it goes through 3D composition steps. One at the top, we break those into the segmentations of what are the objects we also do spatial analytics. In the middle, we look for things like what are the predominant colors, complexities, sharpness, contrast, and various other features. And then at the bottom, we also put this into an embedding space using a clip model. We have an alternate design here using something called hyperdimensional computing, but that's an entirely different talk. And then at the end, we stored our embeddings in a LanceDB in-memory database for vectors. We also use Kuzu, shout out for Kuzu, for our graph database, which is also in memory. And once we have those two together, you'll see these nice little icons of lambs. And that is because our agentic architecture utilizes BAML from Boundary ML, which allows us to ensure that we have deterministic outputs from all of our language model interactions. And more importantly, it allows us to program prompts as functions rather than just messy strings. But more on that later. But at the end of the day, we are able to then query using the agentic system for what are images similar to some topic, like find me images of bananas on a brown table. And that goes through this loop on the right and brings back, in fact, the images. With, most importantly, an actual interpretation for why they are similar. This picture has bananas. It is a picture of bananas, but the bananas are in the same placement as the ones that we have retrieved for you and the predominant colors. And so you get this explainability. Overall, our architecture ensures that we're taking advantage of some of the other features in BAML, and then also what we have developed as far as an overall architecture for when you're working with agents. Right now, we rolled in BAML with a lot of home code. We're in the process of revising this now to bring in other architectures like ADK from Google, and then also as it matures, we'll be utilizing A2A also. Right. What do you want to do this?
Yes, this is just kind of just a kind of a highlight of, or a summary of what David was showing. Kind of more on the word side of things. But so there's these three different basic layers of the architecture itself. Of course, you've got your data layer and your data sources that you're extracting and embedding. And in this case, we're using visual features that are extracted and that with the pre-trained models that we're using. And then we're converting those to vectors in this case, so that we can find the similarity in the next step, which is the semantic layer. And I'd say that's the semantic and graph construction layer. So extracting and embedding, then we do the semantic and graph construction. And that's where you saw on the previous slide where David was showing using Kuzu for the graph, and then using LanceDB for the vectors as well. And then the nodes are connected to represent the image features and metadata like color and position and possibly things like texture. And then you have the query level as well. And so this is where we are looking at both vector similarity for searches, but then graph queries as well to bring in that contextual data. And what I find really interesting is we're kind of marrying the best of both worlds in the state of the art to give us both really nice global and also very local search as well. And then from there, we can look at just a little double click on the semantic and graph layer, because I think that's kind of the backbone of a lot of what we're doing. So if you were seeing this in live in 3D, this is actually kind of a 3D search. So you'll see and we have this actually in a notebook if anybody wants to see it. So you can see basically X, Y, Z coordinates and try to look at from a associative sense what the similarities are for different local areas. So you might say, hey, I'm looking for a bunch of bananas sitting on a wooden table, and you're going to get what is locally the most similar from a vector search comparison. So from there, though, you probably want to look at more of a global, discrete, defined searches as well. And so in this case, we're looking at these bananas in these different images and looking at the spatial relationships. So we've actually, if your eyes are good, you can see is type of, in this case, cup is type of banana. And then you can say is left of, is below, contains, uses color, you get color in there as well. So it actually has a lot of customization you can do. And this is an example of some of that. And so for example, we've got image uses color, contains, above, below, left, right of, and each color can also have a dominant score. We can also look for things like texture. And David, you've got some more details you usually like to share here as well.
Usually Thank you. Around the contains relationship, that's also important. Because remember we said that we have the actual bounding boxes of objects and that we've created a small world network of the spatial analytics of how objects are related to each other in an image. Well, on the contains relationship, you also can do things like looking at what percentage of a bounding box is it of the total image dimension. So now you can have a language model being able to interpret, to that earlier point, is this a picture of bananas because it takes up the majority of the dimensions of the image, or is this a picture that contains bananas because they're a small bounding box?
And so what that allows us to do is really interesting reasoning within components. And so I've just got an image here. So we'll be talking about images, but you might ask questions like, are there ships with similar markings or surface wear nearby? Or maybe that might be identical. What kinds of ships are in the image? Are they moving together? Are they moving apart? Is one taking over another or advancing? And so it gives us an ability to do very robust contextual understanding. How are placements? What are movements? What speed are things potentially? It also gives us very precise object recognition, as you can imagine, because you're looking at not just, is it a similar vector, but is it in context? Is the pattern similar? Is the hierarchy similar? Those are some of the typical graph reasoning we can do with images. There's also a lot of nuanced similarities you can do. So you can imagine we're looking at similarities, you get a lot of gross similarity, but you also might want to customize that. Some of the things that David was just talking about, the detail you could customize in the graph representation of the image itself. And then of course, if you want to understand why you're getting a result and you're saying, hey, I think this is, I'm going to make this up. I think this ship is speeding up. Maybe let's say speeding up, yeah. And is trying to overtake, this other vessel. Why? Well, you can, using the graph and using the similarity and associative search, you can then have more explainability of why that decision was made. So there's a lot of use cases that this allows us to do. Imagine geospatial analysis. Give me the red roofs near water in this time frame. That can be very difficult to do, but if you can get that context, both globally and locally. There's of course a lot of surveillance possibilities is here. So you might want to look at similar objects that have similar markings that are in the right spatial dynamic of particular images. Medical diagnosis, well, I'll show an example of that in a moment, but you could look for certain markers and abnormalities in images. You can imagine, how important that could be. I would say IP search as well. So if you're doing patents, and what do patents have in them? They have lots of images, right? And how do you compare not just what's the words that are in the patents, but the images as well? And so you might want to compare a new design for similar images in old design. Make sure you're not doing something, that's already been invented. Recommendations, I think that's pretty clear how that would go. I'm looking for a cheap trowel with a yellow handle. So I want just not a particular item, but I want also items that are similar or associated with that as well. And then archival data management, I hadn't thought of this, something actually David brought up, was if you think about historical context or context pre and post war scenarios, being able to catalog images from older images to current images to hopefully what it would take to rebuild or reinstate things, having those complex visuals are very important. So some cool things we can do, and David's actually going to preview something even cooler.
So quickly, to make sure that we have some time left over for questions, because we're interested in your questions, we realize there's one more decomposition step that you can do, especially in the medical domain, but this applies in other domains as well. In the medical domain, there are three-dimensional images for things like CTs and MRIs. Those are made up of a special kind of pixel called a voxel. It has an X, Y, and Z component. If you think about X, Y, and Z, that means that a pixel has a Z neighbor, an X neighbor, and a Y neighbor. You can do a lot of interesting things. And at the end of the day, you can make a graph of a brain. And now you can treat a brain as if it were a database, do cluster similarity and analysis, and then start to isolate things like tumors or lesions, and then start to ask what is their adjacency to neuroanatomical structures, and the list goes on. So we've developed, this is some work we did earlier. This is brain graph. But now we're also starting to inject in audio, because audio gives you the ability to see out of scene objects for segmentation that weren't visible, but were in the environment. Also, interestingly enough, people, I think, skip over the fact that audio gives you temporality. So you can actually inject temporality into a static image. If I'm looking at a scene of a park, but there's some train tracks behind me, and I hear a train, well, first I can segment that there is a train. Second, as I do interaural detection, I can tell from left to right what direction the train was going and what potentially what speed it was going, because I can look at the duration of the audio and the loudness going from the left channel to the right channel. So a lot of interesting things you can do there. Finally, I'll mention that you can take the data out of graph. And we've been working with the team from NVIDIA around NetworkX, which now allows you to do analytics and graph data algorithms in CPU. Then when you're ready to go to production, that same code works on GPU. So we're really excited about that as well. And I think that brings us to the right slide.
Thank you.
Yes, I'm Margaret Warren. I created image snippets, which actually has made an image graph as well, from mostly from context, a lot from context. So I'm really curious to know